Hi everyone, welcome back. So for the fifth question on the worksheet, we have mechanical discretization. So if we have the following relation between the input voltage and the velocity, so U of t is just the input, and the V of t is the velocity of the car that you're trying to build. Let's say that U of t is constant during each interval, nt, n plus 1 of t. We want to analyze our velocity in discrete times as follows. So we're just going to cut these times into discrete times to get a relationship in the form of Vd of t plus 1 is equal to alpha Vd of t plus Ud of t. So apparently, the t here has a different meaning than the t in a differential equation above. The t right here represents time steps, whereas the t on the top represents continuous time. As always, if you want to work on a problem on your own, you might pause the video for like a couple of minutes, try working on it on your own, and 3, 2, 1, unpause. So for this very first question, we want to find Vt plus t in terms of Vt and U of t. Okay. So there's a hint that says we want to integrate both sides and apply the fundamental theorem of calculus. So if we try to integrate both sides, we'll try and integrate both sides. We integrate both sides to get t plus t dv being equal to integral from t to t plus t 5 u of tau d tau. Okay, note that we have to change from t to another variable because it will look super confusing if we keep using t right here. All right, so then we just use the fundamental theorem of calculus. Just find the antiderivative of things. See that the antiderivative of dv, which is vv. So we have vt plus t minus vt being equal to 5, since u of tau is constant between t and t plus t by assumption. So we see that this is actually equal to 5 u of t plus t. So the antiderivative of this whole thing is actually equal to 5 u tau tau, because u of tau is a constant. Okay, so this is a constant. And then we just use the fundamental theorem of calculus to see that this is actually equal to 5 ut plus t times t plus t minus 5 ut times t. Right, since ut plus t is equal to ut, we see that vt plus t is simply 5 t times ut plus vft. Okay, so we have found vt of t in terms of v of t and u of t. Okay. All right. So for the second question, it asks us to use the result from part 1 to find alpha and udt in a relation. Okay. So this will be a little bit confusing. Because we're trying to use the two t's at once. We're trying to use the discrete t, and we're trying to use the continuous t. Using the same symbol. Will be confusing. But if we use it right, it won't be too confusing. So for the sake of this problem, let's just say that Vd of t is just v of t. And that Vd of t plus 1 is just Vt plus t. Okay, that is 1 in terms of discrete time step is just t in the continuous time. Okay, This will be confusing. This is very confusing. So typically, what we typically do is that in terms of discrete time steps, we use k like another variable instead of t, so it doesn't become too confusing. So after we made these substitutions, we would then have vd of t plus 1 being equal to vd of t, because we have that being equal to v of t plus 5t times u of t. So plus 5t times u of t. In the context of this question, the integrations that we're trying to do, it isn't too complicated, but we do need to have a conceptual understanding as to the difference between a discrete time step and the continuous time. Okay? So that concludes for part A of this question. So now, off to part B. Now we want to examine our car's position in discrete time, knowing that the derivative in distance is just the velocity at a given time. So we want to integrate both sides to get x t plus t in terms of x of t, v of t, and u of t. Okay. So to do that, we notice that we can use the fundamental theorem of calculus to see that the integral or the antiderivative of a derivative is just itself. So take the integral of this whole thing, t plus t. We just take the integral from t to t plus t, dx of t. Let's just write dx for simplicity. On right hand side, we're also integrating over the time t to t plus t over v of t. Obviously, we cannot be reusing the symbol t. So again, we're just resorting to tau. Okay. And what do we know about v of tau during tau, when tau is greater than or equal to t and is less than or equal to t plus t? We do know that dv dt is equal to 5u of t from part A, okay, where u of t is constant during this period, right? So in that case, we can write v of tau. So it's just like a straight line. If you draw it out of the coordinate system, just like a straight line, with the slope being 5u of t during this period of time. So let's say this is t, and this is t plus t. Obviously, this is probably not the right, we can't have a negative t, but this is a little bit sketchy, but it should do it. So basically, since the slope is like constant, we see the v of tau is equal to v of t plus v prime of t times tau minus t. Okay, so this is not something that's generally true. This is not something that's generally true. In later sections within 16B, you'll see techniques like this that are used to approximate the value of v of tau, but they're not equal. In the context of this question, since the derivative is always constant, we know that these two values are just the same. All right, so we see that the left-hand side is equal to x because the antiderivative of 1 is just x. X of t plus t minus x of t is just equal to the integral from t to t plus t, v of t plus v prime of t, tau minus t, d tau. Okay. So on the right-hand side, we have v of t and v prime of t, which is equal to 5 times u of t times negative t. Like these two terms, they're both constant with regards to tau, as tau goes from t to t plus t. Okay, so we see that this is just equal to v of t plus 5, actually minus 5t u of t times t. So I have the integral. It goes from t to t plus t of 5 u of t tau d tau. So the antiderivative of tau is just 1/2 times tau squared. And so this is equal to v of t minus 5t u of t t plus 5/2 u of t tau squared taken over tau. Tau equals t all the way to t plus t. Okay. And so this is equal to v of t minus 5t u of t t plus 5/2 u of t times 2tt plus t squared. Okay, so we realize that this 2tt term, multiplied with this 5/2 times u of t, just cancel out with this term. So we see that it's equal to t times v of t plus 5/2 u of t t squared. And that is our answer for part 1. Okay, off to part 2. We want to find alpha, beta, and ud of t in the following relation. Okay, so similarly, we just obviously again there's a difference between the continuous t as opposed to the discrete t, but we have to work with it. So again, we set xd of t to be x of t, and we set xd of t plus 1 to be xt plus t. So again, we are setting the unit time step in a discrete time to be t, the uppercase t, as in the continuous time. Okay, so we just say vd of t is equal to v of t. So apparently the t on the left is a discrete time step, but the t on the right is a continuous time. The same logic goes for ud of t, but since there isn't a coefficient around ud of t, we can't really just say that ud of t, we set it to be u of t. It really doesn't make any sense. Okay, so we just plug in equations to see that xd of t plus 1, the discrete time, the discrete distance at this time step t plus 1 is equal to xd of t plus t times v of t, actually vd of t, plus 5/2 u of t t squared. And so it then follows that the desired values that we're looking for here are alpha equals 1, beta equals t, and ud of t is equal to 5 times ut t squared, actually over 2 right here. All right, so I think in the context of this question, we explored how we can turn a continuous relation into a discrete relation and try to make the most out of it. So in some of the systems, doing a discrete system might be more convenient than doing a continuous system. And we have realized a way to actually make that happen. All right, that concludes our walkthrough for question number 5 on this worksheet. And since question number 5 is the final question on the worksheet, that also concludes for our walkthrough for worksheet number 2 for CSM 16B, spring 2021.